In this simulation, we are using Astrogator in Systems Toolkit STK by ANSYS, simulating the Apollo 11 mission. This exercise is part of our broader project paralleling the NeoVision lunar mission's concept of operations. We begin with the launch view using the SpaceX Raptor rocket. Our spacecraft, equipped with the hybrid propulsion system, ascends, overcoming the Earth's escape velocity and enduring the max Q. After jettison of the solid rocket boosters and achieving main engine cutoff, we enter a preliminary Earth parking orbit. We revolve around the Earth till we reach the strategic staging point for the trans-lunar injection. The trans-lunar injection is a pivotal maneuver. Here we calculate the trajectory to align with the Moon's orbit. During the cruise phase, our spacecraft is continuously monitored. Small but critical mid-course corrections are made to refine our path. As we approach the Moon, the lunar orbit insertion burn is executed, slowing our spacecraft to be captured into the Moon's orbit. Upon reaching the lunar orbit, we enter the lunar circularization phase, a critical yet gradual process. Over several days, the spacecraft adjusts its orbit, aligning precisely with our designated landing site as the Moon rotates and the spacecraft revolves around it. This involves continuous monitoring and minor adjustments responding to the Moon's uneven gravitational field. This phase is crucial yet often understated, sets the stage for the subsequent lunar descent. Now we direct our attention to the lunar descent module. Unlike the Apollo 11 mission, where the lunar descent module is a separate entity from the command module that remains in orbit, our spacecraft commences its descent phase as a unified structure. This positions our spacecraft for a controlled descent onto the lunar surface. Our simulation will now describe the descent phase, including the touchdown in great detail, showcasing the complexity and precision inherent in this STK simulation. The descent phase of our lunar mission begins with the landing preparation phase, where the spacecraft aligns for the descent. This is followed by the main deceleration phase, reducing velocity for a controlled approach, and the adjustment phase for the fine-tuning trajectory based on the real-time lunar observations. Finally, the slow descent phase ensures a careful touchdown. Our landing site is strategically chosen for its high helium-3 concentrations, typically found in the far side Maria and the near side Maria regions, with higher titanium dioxide content in the lunar regolith, significantly contributing to the higher helium-3 content in this region. After completing the extensive multi-year mining operation of the helium-3 and accumulating adequate energy reserves from the hydrogen, we initiate the ascent phase. Our module, distinct from the Apollo mission's docking strategy, launches directly onto the low lunar orbit. It means that it remains in this orbit, revolving around the Moon to align temporally and spatially with the trans-Earth injection to begin its homeward journey. In our simulation, we've adapted certain aspects of the orbit to fit the available data, ensuring an accurate yet imaginative representation of this stage. We observe that the trans-Earth injection also involves some course corrections. As we prepare for re-entry to the Earth, the focus shifts to the re-entry phase, and the separation of the re-entry module along with our payload and critical heat shield is simulated, which showcases the process of abrading away excess heat upon re-entry. We now transition to the parachute deployment phase, showcasing the last mid-course corrections, replicating historical data. Following this controlled descent, our module touches down on the ocean surface, where a recovery vessel is positioned to retrieve it, marking the successful completion of this mission.